Hello, welcome to this video of vectors. In this video we'll be looking at the line. The line is a straight one-dimensional figure without thickness that extends endlessly in both directions, like this black line that we have here. Now in 2D geometry we look at the x and y axis, and the equation of a line is given as y is equal to mx plus c. In other words, c and m help us define this line. C tells us that the line passes through a point 0c, and m tells us that the line is inclined to the x-axis through an angle theta, where m is equal to tan theta. And so m and c in that way give us the direction of the line and a point that the line goes through. Now in 3D geometry we will need those two, the direction of the line and a point that the line goes through, to give us the equation of a line. So we have the vectors a and b, which are position vectors of points a and b, and then a point p that sits on the line that goes through points a and b, where p is an arbitrary point whose position vector is r. Now from that we can see that ap is equal to lambda times ab. Since the points ap and b are collinear, that means that ap has to be parallel to ab, and so this equation must hold. We know that OP minus OA is in fact AP, and AB is in fact OB minus OA. And so this tells us that R minus A is equal to lambda times B minus A. And so R is in fact A plus lambda times B minus A. But what is B minus A? B minus A is a vector that stretches from one point on the line to another point on the line. B minus A could be any could be any vector between any 2 points on the line. So we write R is equal to A plus lambda times D, where D is called the direction vector that stretches between any 2 points on the line, because any 2 points on the line will have a vector that has the same direction ratio, because all those vectors are parallel. And so R is equal to A plus lambda times D, where D is a direction vector and A is a point that lies on the line. And so we have maintained that we have used the direction vector, we have used the direction of the line and a point that lies on the line to define the equation of a line. Now this is the vector equation of a line, and there are other forms of equations of lines in 3D geometry, such as the Cartesian form, and we will get this from the vector equation of a line. We had that R is equal to A plus lambda times D. Our D was B minus A, and we can write our R as x, y, z because it's an arbitrary point that lies on the line, and we'll write our A as x naught, y naught, and z naught, saying that A was at x naught, y naught, and z naught, and our B was at x1, y1, z1, so this will be x1 minus x naught, y1 minus y naught, and z1 minus z naught. Now if we take the position vector of A to the left, we'll have y minus y naught, sorry, x minus x naught, y minus y naught, and z minus z naught being equal to lambda times the direction vector, which is x1 minus x naught, y1 minus y naught, and z1 minus z naught. Now if we break down this into three different equations, we'll have this x1 minus x naught, we'll have y minus y naught is equal to lambda times y1 minus y naught, and the same thing for z. Now from these three equations we can get three different expressions for lambda. We'll start with x minus x naught out of x1 minus x naught. This is equal to y minus y naught out of y1 minus y naught, and this is equal to z minus z naught out of z1 minus z naught. And this is the Cartesian equation of a line. Now the lambda is equal to part is not always included, and it can be left out, but these other three expressions have to be there. And you realize that in the denominators of those three fractions we have the direction vector. We have x1 minus x naught, y1 minus y naught, and z1 minus z naught. And in the numerators being subtracted from x, y, and z, we have a point on the line, x naught, y naught, and z naught. And so as long as the coefficients of x, y, and z in the three fractions are positive 1, then we can extract a point on the line from the numerator and the direction vector of the line from the denominators. Okay, and there's one last form of the equation of the line, which we get from these three equations, and that's called the parametric form. It simply comes from making x, y, and z the subjects in those three equations. And so we have x is equal to lambda times x1 minus x naught plus x naught, y is equal to lambda times y1 minus y naught plus y naught, and z is equal to lambda times z1 minus z naught plus z naught. Again, you can see that you can extract a point on the line from the terms that are free of lambda, and then the terms that are attached to lambda will give you the direction vector of the line. Okay, let's look at an example of from which we can get the equation of a line. So find the equation of the line that passes through those 2 points A and B. So we have those 2 points. The first thing we could do is get the direction vector of the line, which, like I said, is a vector between any 2 points on the line. In this case, we already have the 2 points, so we can go ahead and get the direction vector straight away. We know that AB is OB minus OA. OB in this case is 1, negative 2, negative 5, and OA is 1, 3, negative 1. So this will give us 0, negative 5, and negative 4 as the direction vector of the line. Okay, so now that we have the direction vector, we can go ahead and write it in vector form. R is equal to OA, in this case 1, 3, negative 1. You could use OA, you could use OB, it doesn't matter, plus lambda times 0, negative 5, negative 4. And this would be the vector equation of that line. However, you could write it in parametric form. You know that to write it in parametric form, this would be x minus 1 out of 0 is 0 is equal to y minus 3 out of negative 5 is equal to z minus negative 1, so it becomes plus 1 out of negative 4. The dividing by 0 simply tells us that the direction vector is 0, negative 5, negative 4. So in this case, it's not undefined. Yes, and of course you can see that there is a point on the line that is 1, 3, negative 1, and the direction vector is 0, negative 5, negative 4. Yeah. However, you could also write this as x minus 1 out of 0 is equal to y plus 2 out of negative 5 is equal to z plus 5 out of negative 4. You could use the point B instead, it also doesn't matter. So this is the Cartesian forms. You could also have the parametric form. Parametric form, you can see that you have x is equal to 1. You can get that from here. X is equal to 1, y is equal to 3 minus 5 lambda, and z is equal to negative 1 minus 4 lambda. This also works. So that's how we get the equation of a line.